You know how sometimes a computer gets a math problem wrong? It's super weird, right? I mean, these are machines built for perfect calculation. Well, today we're going to dig into why that happens. And it all comes down to the most fundamental building block of computing there is, the bit. And you'll see, this one super simple idea, it explains, well, pretty much everything. Okay, so here's the plan. First, we're going to look at this weird little glitch called the F32 anomaly. Then we'll get right down to it. What is a bit? Spoiler, think of it like a light switch. After that, we'll see the insane power you get when you start combining those switches, how that lets computers handle numbers, and finally, how that simple idea builds our entire digital world. It's going to be fun. All right, so let's dive into our mystery. In the world of programming, there's this super common way to handle numbers with decimal points. It's called an F32, or a 32-bit float. But here's the weird part. Sometimes when computers do math with these F32s, they spit out these tiny little errors, these glitches that honestly just don't make any sense. So what's going on here? Why would a machine that's built for precision get things even a little bit wrong? And the answer, which is really cool, isn't some complicated software bug. Nope, it's something way more fundamental, something baked right into the architecture of how computers, well, how they think. And believe it or not, the first big clue is hiding in plain sight, right there in the name, F32. That number, 32, that's the key. It stands for 32 bits. And you guessed it, to crack this case, we have to figure out what on earth a bit actually is. Okay, this brings us to the absolute ground floor of computing. I mean the bedrock. We're about to look at the smallest possible piece of information you can have. You could call it the atom of the digital universe. We are, of course, talking about the bit. So the official definition is pretty simple. A bit is the smallest unit of data in a computer. It can only hold one of two values, a 0 or a 1. That's it. Simple, right? But what does that actually mean in the real world? What does it look like? Honestly, the best way to think about a bit is to picture a simple light switch. Seriously, it can only be in one of two states, right? It's either off or it's on. That's it. All we do is give those states a number. We say off is 0 and on is 1. And that's all a bit is, just a simple two-state system, off or on, 0 or 1. Now, one little switch all by itself, it's not super useful, right? It can only be on or off. But what happens when we start adding more switches? See, this is where the real magic of computing begins. So let's think about it. If one switch gives us two states, on or off, what do you think happens when we have two switches? How many different unique combinations or patterns can we possibly make with two of them? Well, with two switches, we can make exactly 4 unique patterns. Think about it. You can have both of them off, you can have both of them on. You can have the first one off and the second one on, or you could have the first one on and the second one off. And that's all the combinations there are. We've just doubled our possibilities, going from 2 to 4. And this simple example actually reveals a super important rule. The number of patterns you can make is always 2 to the power of the number of switches you have. So with our 2 switches, it's 2 to the power of 2, which is 4. The big thing to remember is that the number of switches you have, that becomes the exponent. And once you get that rule, you start to see how things get crazy fast. If we add just one more switch for a total of 3, now we have 2 to the power of 3. That's 8 patterns. Add another one, 4 switches, that's 16 patterns. 5 switches, 32 patterns. Every single switch we add doubles the total number of possibilities. It's exponential growth. Okay, so let's tie this all the way back to our F32 mystery. Remember F32? That means 32 bits, or 32 switches. So if we apply our rule, 2 to the power of 32, how many unique patterns can we make? The answer is just mind-blowing. It's roughly 4.3 billion. Billion with a B, from just 32 little switches. All right, 4.3 billion patterns. That is a massive, almost unimaginable number. But how does a random pattern of on and off switches actually help a computer do math? What's the connection? Well, let's connect those dots right now. Here's the brilliant part. Every single one of those 4.3 billion patterns is assigned to represent one specific, unique number. Think of it like a giant code book. There's an entry for one number, and it has its own special pattern of on and off switches. It's a perfect one-to-one map. Every number gets a pattern, and every pattern means just one number.
Okay, so let's walk through an example to make this super clear. Let's say you tell your computer, hey, store the number 5.0 for me. What happens inside? Well, the computer instantly looks up the one unique pattern of 32 switches that means 5.0 in its codebook. Then it literally goes and flips its 32 internal switches into that exact configuration, that precise sequence of ons and offs, and that's how it holds that value in its memory.
So now we know how just 32 simple switches can represent billions of different numbers, which is already pretty amazing. But let's take one last step back and zoom out to the really big picture. Because this whole idea, it goes way beyond just numbers.
And this finally brings us back to that F32 anomaly, that weird math error. See, while 4.3 billion patterns sounds like a ton, there are actually an infinite number of real numbers out there. A computer with only 32 bits just doesn't have enough patterns to give every single number its own unique one. So it has to get close. It makes tiny approximations for the numbers in between its patterns. And that's where those little errors, that weirdness, comes from. But the core idea here is so much bigger. It's absolutely profound. Every single thing in our digital world, every photo you take, every song you stream, every piece of information is just an enormous specific pattern of billions of simple switches that are either on or off. All the incredible complexity of our modern world, it's all built on a foundation of tiny light switches just blinking away.